Hello everyone, I hope you're having a wonderful day. Today we are going to talk about the bending test which you performed earlier uh, this week. In general, the discussion we're going to focus on the structures that are used in an airplane. That's the first part of the lecture. We are going to talk about the airframe. We are going to talk about the structural concepts that are used in an airplane. We will talk about the fuselage structures. We will talk a little bit about the torsion box, and we will talk a little bit more about the structural details of an airplane. So the first part of the lecture is gonna focus on these structures and the forces that are being applied to them. So we will talk about the torsion and the bending mainly, and we essentially wanna emphasize on the importance of a beam bending and torsion analysis in an aerospace aircraft design in general. And afterwards, we'll talk about the bending theory and bending tests. We will talk about the bending test that you already have done in the lab. And I'll make sure to upload the lab instructions today as well, as soon as possible. So let's get to the lecture. Airframe. Airframe is defined as the aircraft elements are the aircraft elements that are part of the aircraft structure. In general, airframe is the aircraft or a spacecraft without installed equipment and furnishing. The skin and the framework, including a skeleton that provide the aerodynamic shape, and the load-bearing parts that take off forces during normal flight, maneuvers, takeoff, landing, etc. Also, the parts that together protect the content from the environment. Here we have two examples of one of the earlier aircraft frames that was designed, one of the earliest aircraft that was designed. You can see the aircraft frame there for a Fokker spin or Fokker spider. And on the right hand side, you can see a modern aircraft frame for a modern military jet. It's a Sukhoi Su-25T fighter jet, which is I think it's a Russian jet. But yeah, you can see the development of aircraft. In general, in the earlier stage of the aircraft design, all you had was the aircraft frame. There was no protection, there was no furnishing, there was no nothing else. Right? But in the modern aircraft, the aircraft frame is essentially a cover for whatever that is inside. So again, aircraft frames can be divided into two different categories. First one, primary structures. Primary structures are the elements that fulfill a critical function that in case of damage or failure could lead to a failure of the entire aircraft or a spacecraft. And secondary structures are structural elements that fulfill non-critical functions, and they can carry only aerodynamic and inertial loads generated on or in the secondary type of structures. Right? So let's talk about the structural concepts that are used in aircrafts in general. And these are the concepts that I assume you have seen before or you're familiar with. These are not very special concepts, but they are definitely used in the aircraft. The first structural concept is a truss structure. Truss was actually the most widely applied structure in the earliest parts of aircraft design, and in some other industries, it is still the most widely applied structural concept, like the railway bridges, right? But nowadays, truss is being used a little less and less in aircraft designs, and it's being replaced by other type of structural concepts. Which essentially, a truss is a very simple wire bracing of a structure. Early aircraft were built with trusses, as mentioned. Load is transferred via tension or compression. diagonal function in charge of we need to add a diagonal function that should be in charge of structural rigidity. As an example, we have the truss structure with a wire at the diagonal as the diagonal function. So if you have the wire this way, it will be resistant to any sort of compression in this direction, but it won't be able to resist any sort of tension in this direction. These are actually shear forces. So truss cannot withstand any sort of shear force. So that's the problem with truss. That's why we end up adding plates in the truss structure. But examples of the truss structures that are still being used in the aircraft industry can be seen here. We have the diagonal support as well. This is actually an example of the space shuttle, and the truss structures you see here are using the boron aluminum as their material. So this is the ribs in the center fuselage section of the space shuttle. So truss is still being used even in the space shuttles, but it is not the most widely used structural concept anymore. The next structural concept we want to talk about is the shell concept, which essentially shell is simply the application of sheets in truss to fulfill the diagonal function that we used to fulfill with just a diagonal wire. Sheet performs in shear versus rods and wire who can only perform tension. We have thin wall sheet structures that can perform in tension, compression, and diagonal and shear loading, and also can be used in sealing. Examples of forces that are being applied to a plate: they are very strong for tensile, they are weak for compressive, the sheets, and we can increase their stiffness with just playing with their geometry. But you have to keep in mind that to fully exploit the benefits of a sheet material, it may be necessary to reinforce the sheet with other elements. Without any additional reinforcement, the sheet material can easily carry tensile load, as mentioned, to its ultimate strength, but it cannot carry significant compressive loads. We can always add the stiffness to we can always increase the stiffness of a sheet by changing its geometry, or by adding a geometrical stiffeners, like the hat stiffener in this case. Another example of hat stiffeners. The distance these hat stiffeners have can actually increase or decrease the stiffness of your geometry and the load it can carry. Keep in mind we have different types of stiffeners. And I'm sorry. So using the shell structures, we can actually come with a new structure that uses girders and a web plate. And we will talk about this type of structures a little bit more later on, but the girders and the web plates, or the stringers, are actually used very often in aircraft industry, as you can see in the aircraft example, the fuselage example here. Another type of a structure that is worth mentioning is the sandwich structure. It has a very low density core, and it is going to be between two phase sheets, a sandwich structure. It's the same concept as a beam based on a web plate as the girder, and we're going to see a comparison later on. And normal forces are carried by the phase sheets, a diagonal shear function carried by the core in between the function. But an example of a sandwich structure, as you can see here, right here, we have the phase sheets on top and the bottom, and we also have the core in between. This looks like a sandwich. That's why they call it a sandwich structure. They have the same concept essentially in web plates and girders. The only difference is that between the two girders we have a web plate instead of the core. The structures are bonded. The structures at the core are bonded through adhesion between the phase sheets and the core, actually. Because of that, there's an inherent high bending stiffness in the sandwich structures. But the problem with the sandwich structures is always the durability. It is their Achilles heel because the core is always not very durable. And the other very, very, very important problem, especially in the aerospace industry, is the mechanical joints. So it is very hard to put screws on these sandwich structures because you are going to mess up the core, you are going to destroy the core, which defeats the purpose of having the sandwich structure. An example of sandwich structure, you can see you can compare the stiffness of a sandwich structure with a just a solid material. You can see the stiffness with the same thickness is just 1, but if you add a core in between, if you just divide this by 2 and add a core in between with the same thickness, which means that you are multiplying the thickness, you are going to have a 7 times stronger structure, right? And the flexural strength, which is E multiplied by I, is going to be 3.5 times stronger. The same is true for a 4 times thicker sandwich structure. You will have 37 times a stronger structure, and your flexural strength is going to be 9.2 times higher than just a regular beam. And you also have to keep in mind that the weight has not increased that much, just by 6%, right? Here. But the stiffness has increased 37 times. So the sandwich structures are very, 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 very strong. But the problem we have with the sandwich structure, especially in the aerospace industry, is the lack of ability to deal with mechanical joints, essentially. Okay, another type of structures that have come to wide acceptance and wide use because of the CNC machines are the integrally stiffed structures, which are essentially a stiffed shell structure. We can say a stiff shell structure can be manufactured in 2 ways. First one is mechanical fastening, like riveting, bolting, or by bonding, or even welding, right? But we can also use a thick plate and machine away the extra material, the material between the stiffness. And you can see an example of it right here, right? That's the integrally stiff. That is an integrally stiff structure. So the integral concept has a very low cost. It has an automated process. You can have high volume production at a relatively low production cost, and you will need low amounts of part. You essentially just need a thick plate. That's it. But the problems with this concept is a high amount of scrap material. You will need continuous tailoring, and it is only a single component, which means that there is no natural barrier against cracks, which is also a very important consideration when you're designing an aircraft. Okay, so we can use all of these structural concepts and put them together to create different parts of your aircraft. The first part we want to discuss, we want to introduce, is the fuselage structure, which is a thin-walled pressure vessel. It usually uses the stiffened shell concept. It has different parts, of course. We have the fuselage skin. We have the frames of the fuselage. We have the stringers. We have the bulkheads. And we also have the splices and joints. Longitudinal stiffness in a fuselage structure is created by a closed cylindrical shell structure, essentially, and also the stringers to the skin panels that you have. To increase the rigidity of this type of structure, the fuselage, we want to combine the stringers to longerons, and the pressure steering is done by the bulkheads. Another type of structure that we need to have to be able to fly is the wing. Wings are essentially similar stiffened shell concepts with just a different appearance compared to a fuselage. We have the wings, they have the wings skin panels, they have the ribs, they have the spars. An example of the wings. You can see two examples of the wing structures here. But the question is, what do ribs do in a wing? Ribs maintain the aerodynamic part of the aerodynamic profile of the wing. They are placed in the flight direction. The placement benefits the weight of the wing, which means that you essentially can have a lower weight wing by this type of placement. They are responsible for transferring the aerodynamic and fuel loads acting on a wing to the rest of the wing. So what does it mean? They also provide stability against buckling and panel crushing. But what does these two mean? These two jobs the ribs have is that you're essentially making four different parts of the wing, which means that instead of a huge load that is going to be applied to your wing and the buckling problem that you're going to see, the bending problem that you're going to see, because of that, you are going to distribute this load throughout all of these ribs, and the bending problem will actually can be solved eventually with increasing the number of the wings. So you can have a less stiff and a less strong, or a less strong material by just adding ribs. You're gonna fix the problem of the bending load on the wing. So as you can see, this tells you that we have wing can act as a beam, right? And it is a very important conclusion because it means that you have to be able to do a bending analysis on your wing. And it is not just a wing, every part of the aircraft can act as a wing, right? Using ribs, we are going to introduce local loads. The ribs also function as a ceiling. They also have a ceiling function in case the integral fuel tanks are used. In general, ribs are, when designing a rib, when manufacturing a rib, you have to have the loads in mind. You have to know the design philosophy of the aircraft. You all, of course, always have to know the available equipment and experience, and you always have to be mindful of the cost. But what do spars do in an aircraft? Spars are the structures like this. So essentially, this type of structures you can add in a wing. They essentially have the similar functions to the ribs. They carry the wings bending load. The spars are beams designed to carry bending load, as mentioned before. The basic form of a spar is just a regular I-beam. Girders pick up the normal force, web plates pick up the shear force. So girders are responsible for the normal force, web plates are responsible for the shear force. And they're gonna have they're gonna have the same function as the ribs do. So the deflection, you expect the deflection near the wing root to be significantly smaller, because the wing compared to the deflection near the wingtip, right? And spars are there to essentially distribute this deflection. I mean, the deflection, the distribution of the force, essentially. So the equilibrium between the normal forces in both girders and the spars near the wingtip and the upward bending moment will result in a relatively small force in the wing root, right? Yeah. Okay. So you always get into the manufacturing problem because you need to have a thicker spar near the wing roots. And the final structure we want to talk about is the torsion box. This talks to the torsion experiments we have in the we are going to have in the next couple of weeks. We will talk about that experiment separately, but I just want to mention the torsion box. Okay, so what is the torsion box? What do we use it? So wing loaded by the wing is always loaded by the bending and torsional moments. A single spar cannot carry the torsional moment. So mainly because an I-beam has a very low resistance against the torsion box. So we either can have two I-beams, two spars to circumvent the torsion load that is being applied on the wing, right? Or we can have something called a torsion box. But you may want to ask that, why do we use the torsion box? The torsion box actually exploits the torsional resistance of this closed box structure. So when you have a closed box structure, your structure is going to resist torsion, right, compared to an I-beam. It's going to resist the torsion better than the two spar concepts that we have here. Okay. But we can also, in order to circumvent the torsional load on the wing, we can also have something called the wing box, which is an extension of the idea of the torsion box. Like we have the stiffeners here, we have the hat, the stiffeners inside. We are essentially going to make this material stronger and stronger, right? This is going to be discussed and analyzed in your next lab 2, and we are going to, which AESP 362. we are essentially going to simulate a wing box, a torsional load on a wing box. Okay, so we have talked about the structures, we have talked about the structural concepts and how those structural concepts contribute to different parts of an aircraft. The next part is going to talk about the theory. We understand, hopefully at this point we understand that torsion plays an important role, as well as bending. Bending also plays an important role, but also buckling. We have mentioned buckling, which will be the topic of this discussion later in the semester, the shell buckling of the structures. And yeah, the next step is going to be discussing the theory of bending. Essentially, the first thing we want to discuss is pure bending. Pure bending is we can define the pure bending as a prismatic member subject to an equal and opposite couple acting in the same longitudinal plane. What does it mean? Let's look at this example of a weightlifter in Olympics. So we have two weights here, right? And we have two supports here. So if you want to draw the free body diagram of this weightlifter, it will look something like this, right? Which means that you can actually replace this free body diagram with moments, the forces here with only moments at location C and D, right? We have the reaction forces, we have the regular forces. We can just remove this part and replace whatever we have with this moment. This moment is called the bending moment, which is pretty obvious from the which is pretty understandable. The naming is pretty understandable. It's going to bend your beam. This moment is going to bend your beam. But bending moment is not the only type of this type of load. Actually, is not the only type of load that is going to cause bending or the bending moment. We can have eccentric loading, which is an actual loading which does not pass through the section centroid. And this actually produces an internal force equivalent to an actual force and a couple, right? So we're going to have bending, and we also here we are going to have tension because the load is not passing through the centroid of the device, right? We can also have transfer loading, like the case of this cantilever beam, which is concentrated or distributed on the beam. This also produces an internal force equivalent to shear force and a couple, right? So all of these moments are going to cause bending. The only difference is going to be whether any forces are going to accompany that bending or not, right? And you always have to keep in mind that you can use the principle of superposition here. What does it mean? It means that you can essentially analyze the moments first and then analyze the forces second, do a bending analysis, and then do a tensile analysis or whatever, a tension analysis, right? And just add the two together eventually to get the final result. And we're going to see the examples of this later on, right? So the internal forces, let's go back to the bending. Let's talk about the bending. The internal forces in any cross section are equivalent to a couple. The moment of couple is the section's bending moment. So you can see from statics that a couple M consists of two equal and opposite forces. The sum of the components of forces in any direction is always zero. The moment is the same about any axis perpendicular to the plane of the couple and zero about any other axis. Right? So these requirements can be applied to the sum of the components and moments of the statically indeterminate elementary internal forces. Okay, so which essentially means that sigma of f in the x direction. We have the coordinate system. Keep in mind that this is the x direction, right? Sigma of x in the x direction is going to be 0 based on what we see here. Sigma of my is also going to be 0. And sigma of mz, the summation of all moments in the z direction, are also going to be 0, is going to be equals to m. Sorry, it's going to be equal to the moment. All right, so we're going to use this force and moment balance to find the eventual deflection and find the eventual formulas we want to use in the bending analysis. Okay, so moving on, let's talk about, let's do a simple analysis. Let's see what we get. So bending, on the left side of the screen here, you are seeing a bending with a plane of symmetry in pure bending. You always have to keep in mind that we are assuming the member always remains symmetric, right? And it bends uniformly to form a circular arc. The cross-sectional plane passes through arc center and remains planar. So what does it mean? It means that these plates are always gonna be just regular planes, right? They are not going to change the shape. That's the assumption. And the length of the top of the beam decreases, the length of the bottom of the beam increases, which means that we always have to have a neutral surface. So a neutral surface in this direction, of course, must exist that is parallel to the upper and lower surfaces, for which the length does not change. So that is a very important conclusion, as you're going to see later on. And keep in mind that the stresses and strains are negative above that neutral plane and positive below that neutral plane. Okay, so let's try to formulate what we already said. Consider a beam segment of length L. After the deformation, the length of the neutral surface, this one, is going to remain L. Okay, and then we want to find the length at an arbitrary location that has a y distance from N. Keep in mind that the radius of this curvature is from the center of the circle to the location of the neutral plane, right? So we have the curvature rho, and the question is, how can we find this L prime? This L prime is an arc, of course, and we can find an arc length using theta multiplied by this radius here, which is rho minus y, right? Your curvature minus the distance from the neutral axis, distance of that arbitrary location, that arbitrary plane from the neutral plane, right? So that L prime is going to be rho minus y multiplied by theta. And deflection can be calculated by delta. This is essentially going to be your new length, which is L prime minus L. So we're going to have rho. We're going to substitute this here, and L is the arc length, which is rho theta itself. So we're going to have rho minus y theta minus rho theta. These two will cancel out, right? And you are going to get negative y theta for deflection. So deflection is a function of the distance from your neutral plane as well as this angle. So based on this, we can actually find the strain. The strain is going to be the change of length, right, which is delta over L, which means that L is rho delta, your deflection is y delta, so your strain is going to be negative y over rho. So essentially, we don't need to find the theta here anymore to find the strain. And keep in mind that the strain varies linearly with the distance from the neutral plane, okay? And then your maximum strain is going to happen at the maximum distance from the neutral plane. So the maximum distance from the neutral plane is going to be distance of one of these surfaces from the neutral plane, okay, and we will call that distance C. So the maximum strain is going to be C over rho, which means that we can find the curvature if you know the location of the neutral plane and you know which distance is the maximum distance, which distance from which surface is the maximum distance. You can essentially, by knowing the maximum strain, you can essentially find the curvature. But we can also find the relationship between the strain at each location and the maximum strain. Just plug in, it's just play with this. If you play with these formulas a little bit, you can find this relationship. Epsilon of x is equal to negative y over c epsilon of m. And this is only true for a linearly, the next part is only true for the linearly elastic material. If we have a linearly elastic material, we know the relationship between the stress and the strain. It's just a stress is going to be equal to E multiplied by epsilon of x, which means that you can find your stress as a function of maximum strain. You can actually replace these two with a maximum stress as well, which means that you're going to find a relationship between your stress at each location with your maximum stress, and they're going to change linearly. And negative y over c multiplied by sigma of m. So let's go back to the static equilibrium, the equilibrium functions we had, equations we had in the previous slides. The sigma of f forces in the x direction is going to be equals to 0, which means that the integral of sigma x dA must be equal to 0. We can replace sigma x dA with this, which means that we can take all of these out because these are all constants for each beam, right? Which means you get to this equation for the force balance, right? We also know that the first moment with respect to the neutral plane is always 0. Is 0, which means that the neutral surface must pass through the section centroid, right? So we're going to do the m of z. We're going to use the third equation we had in the moment balance, actually. We're going to use m of z. We have the moment. It's going to be equal to the integral of negative y multiplied by sigma x dA. We're going to replace sigma x by y over c sigma m, which means that you can take sigma m and c out, right? So m is going to be equal to sigma m over c integral of y squared dA. This y squared dA is the definition of moment of inertia. So we're going to replace that with an I. So your moment is going to be equal to, is going to be related to your tension using this by this equation. Or we can find, or we can say, we can actually rearrange the equation. We can say we can find the maximum stress as a function of moment, the distance, the maximum distance from your neutral surface or neutral plane divided by the moment of inertia. We can also define S as I over C. We'll talk about this in the next slide, in the next page. Which essentially is going to tell you that you can find the tension at each location as a function of moment, negative my divided by I. So this is the bending stress. Okay. The maximum normal stress due to bending, as we said, is going to be mc over I, which is equals to m over s. I is the section's moment of inertia, and we define S as the section modulus, which is defined as moment of inertia over your C. A beam section with a larger section modulus will have a lower maximum stress, and you can actually consider a rectangular beam cross section like the two we have here. For these, your S is gonna be equal to 1/6 A multiplied by H, right? Between the two beams with the same cross-sectional area, the beam with a greater depth will be more effective in resisting bending, right? And structural steel beams are designed to have a larger section modulus. So essentially, an I-beam is designed to have a larger section modulus compared to a rectangular beam. And keep in mind, because you have to deal with two I-beams essentially, two different types of I-beams. Just one I-beam with two different moment of inertia, I guess, right? You can always read the moment of inertia of an I-beam with a specific geometry from the tables, right? I'm pretty sure if you Google I-beams moment of inertia tables, you will see tons of tables. But if you have the book, if you also have the book of for the mechanics of solids, you can go to the appendices of that and find the I-beam moment of inertia. Okay. So let's continue the discussion. Let's see how much further we can go. The transfer, it's also very important to keep in mind that when you have a bending moment that is going to bend your beam in this direction, right, you will definitely have a deflection or deformation in the transverse cross section, right? As it is very obvious in this picture. So but then the question is, how can we find this transverse deformation? Okay. We had this equation, right? We had the relationship between sigma m and c, right? Which we can replace a strain by tension using the Hooke's law, right? And then we can replace the maximum tension using the bending equation we just derived in the previous section. So which means that we can find the curvature using the moment and Young's modulus and I, right? But how can we find the strain, the transverse strain essentially, or the transverse deformation? We can use the equation we have already had. We can actually combine them using nu, right? Which says that the transverse strain is going to be equal to negative nu multiplied by epsilon of x, which is the strain in your moment direction, right? So we can replace epsilon of x with nu y we can replace epsilon of x with y over rho. So your equation is going to be epsilon of y is nu y over rho. So this, let's say we want to find the strain, the epsilon of y, the transverse strain. This location, this is going to be your y, right? But the curvature is your regular curvature, so you don't need to find the rho prime, which is the curvature in the transverse direction, right? And with having the curvature and y and the nu, you can definitely find the strain in the other directions. It is also worth mentioning that the expansion above the neutral surface, there is always an expansion above the neutral surface. As you can see, this is expanding, and a contraction below it, which means that you're going to have an in-plane curvature of rho prime, which is related to your regular curvature, and is called an anticlastic curvature. But let's talk about I-beams a little bit more. Let's watch this video clip for the I-beams, and let's see how we can play this.
Why are I-beams shaped like an eye? Have you ever actually taken a moment to think about this? This simple technology forms the basis of all our largest structures, and even features in one of the world's most famous photos. But after asking some of my friends, few actually knew the answer to this simple question. The I-beam is designed in that way to handle a maximum bending load while using the least amount of material. Let's look at an I-beam supported on either end to understand more. When we apply a uniform load across this beam, the max deflection will occur here in the middle. We can calculate the deflection with this equation. This may look complicated, but it really isn't. W represents the uniformly distributed load in terms of newtons per meter. L is the span between supports. E is the Young's modulus, which, as explained in my Material Properties 101 video, describes the stiffness of the material. But the variable we want to focus on is I, which represents the second moment of area, sometimes called the moment area of inertia. This describes the shape of the beam. More specifically, it describes how the material is distributed throughout the shape. These two shapes have the same area, but that area is distributed very differently, and that is very important. A seesaw is a good analogy for this idea. When we place weight in the middle, it is very easy to lift. In fact, if we place it exactly over the middle, we aren't lifting it at all. But the further we move that weight to the end, the more difficult it is to lift, due to the increasing leverage. A very similar thing happens with beams and bending. Material at the center of the beam, which is called the neutral axis, does not resist bending, and the material furthest away from the center resists bending the most. It is called the neutral axis because if we place a bending load downward, the same way we did before, the beam will bend in a way that will cause the lower edge to be in max tension and the upper edge to be in max compression, and the values of stress gradually decrease to zero at the neutral axis, where there is neither tension or compression. Because the tension and compression is maximum the furthest from the neutral axis, we want to maximize the amount of material on the outside of the profile, where it is needed most. The more material further from the neutral axis, the larger the second moment of area will be. Applying that to the equation, we can see that a larger second moment of area would result in a smaller deflection. So if we place this section under the same bending load, it would actually be stronger if we flipped it over 90 degrees, because now more material is located further from the neutral axis. We could make it even stronger again by reducing this thickness to a minimum, just enough to resist the shear stress, and placing that material at the top, and suddenly we're back to the I-beam shape. You can see this idea put into action all around you. In my last video, I mentioned just one of them, when I spoke about the Willis Tower using a bundled tube structure. This structure maximizes the amount of steel on the outside of the building to maximize its resistance to lateral bending from wind and other loads. I will be talking about another application of this technology in my next video, and if you can think of any other examples of this.
Okay. So moving on, I think at this point you understand the importance of moment of inertia, and this is something that you should have seen in your mechanics of solids course as well. So, but you can always let me know if you have any questions. Let's talk a little bit about the plastic deformations of the members with a single plane of symmetry. It is very important to make sure that you understand this, that the fully plastic deformation happens at a very later stage. And when you have a when you apply a very high load essentially, and when you apply a fully plastic, when you are in the fully plastic region, the neutral axis cannot be assumed to pass through the section's centroid anymore, right? So we're gonna have a resultant R1, R2 of the elementary compressive and the tensile forces from the couple, right? And the neutral axis is gonna divide the section into two equal areas, but we don't know if we don't know the location. So that's one of the goals in the plastic areas. And the plastic moment of the member can always be calculated as 1/2 of A, which is your total area, sigma Y, which is your tension, and D. So, and when you're dealing with the plastic zone, you always are gonna have residual stresses. Plastic zones usually develop in a member made of an elastoplastic material if the bending moment is large enough. So it is very important to know that we start by having a small plastic zones, then the plastic zones will spread and you eventually get a full plastic bend, if you will, right? But those plastic zones is gonna be resulting in the residual stress, and when you're unloading the stress, if you have some of these plastic zones, you are not gonna have a fully elastic transformation. Those plastic zones, of course, are gonna have residual stresses, and you're gonna see some elongated zones in your beam eventually. Okay. Another type of loading is the eccentric axial loading in a plane of symmetry, right? That's going to cause we are going to have two types of stresses. The stresses due to eccentric loading can be found by superposing the uniform stress due to eccentric load and the linear stress distribution to the pure bending. So at this location C, we are going to have a moment and a force, right? So as I said, using the superposition, we can divide it into two different conditions, bending and the tensile stress. The tensile stress is going to be P over A. The bending stress is going to be negative My divided by I. And the distribution of the stress for the tensile one is going to be looking like this. The bending is going to look like this. Just add the two. Let me actually change this to a pointer. So the bending is going to look like this. The distribution of the regular one is going to look like this. You add the two, you are going to get this type of distribution. So it is very important to note that when you are dealing with two type of forces, you just have to separate them, analyze them separately, and just add them up. That's it. But not all loads are symmetrical, so we may have unsymmetrical bending, and which talks about the loads that the couples that are acting in the plane of symmetry, that are not acting on the plane of symmetry. The members remain symmetric and bend in plane of symmetry if your moments are applied in the plane of symmetry. And the neutral axis of the cross section usually coincides with the neutral axis of couple. But if you consider a situation in which the bending couples do not act in a plane of symmetry, you cannot assume the member will bend in the plane of the couples. It is very important. So you're going to have an out of plane bending, essentially, right? In general, the neutral axis of the section will not coincide with the axis of the couple. So how can we analyze this? If you wish to determine the conditions under which the neutral axis of a cross-section of an arbitrary shape, I'm sorry, I'm just reading. So the first thing you want to do is to take a look back at the symmetrical loading. We are going to have a resultant force, and the moment in one direction is always 0, and the moment in another direction is going to be always applied to the couple moment, right? The neutral axis usually passes through the center. We have gone over this. We have covered all of this, right? But what will happen if you have unsymmetrical bending? You have to use the superposition, right? So essentially, you are going to find this theta, right? Which is the angle your moment makes with your plane of symmetry, if you will, right? Then you are gonna find the moment, the component of that moment in this direction, and the component of moment in this direction, using cosine and sine functions, right? Which means that your mz is going to be equal to cosine of theta, and my is going to be equal to sine of theta, and then you have transformed your unsymmetrical bending to two symmetrical bending. You do the calculations for each one separately, and eventually you find the bending stress using an unsymmetrical moment. Okay, but then the point was, we don't know where the neutral axis is anymore. It is not going to be in the same plane as the moment anymore, right? So how can we find the neutral axis? The only point that we can always go back to is the fact that the neutral axis has a 0 sigma of x, right? Has a 0 tension. So you just plug that in the equation. mz is always equals to m cosine of theta. You already have the theta, right? And y is m cosine of theta. Just add the two up, right? Must be equal to 0. You should be able to find an angle that the neutral axis make with your plane of symmetry, whatever that is, wherever that is. Okay, as a function of moment of inertia in the two directions, because we have two moments, right? And the tangent of that theta. So essentially, if you have the moment of inertia, if you have a irregular bending moment, right, which is not applied to the plane of symmetry of your beam, and you are interested to finding the neutral axis or neutral surface, the location of the angle that makes it a plane of symmetry, you can always find the moment of inertia in the two different directions and find the angle your moment makes with your plane of symmetry, and you should be good to go. So far we have talked about the regular bending, deflection, the symmetric bending, the easiest one. We have talked a little bit about classic deformations. We have talked about the superposition, and we also have talked about the unsymmetrical bending. The next part is going to be the discussion. We're going to focus on how to design the bending, a beam, essentially, right? The objective in a beam design is to analyze and design a beam. The objective here is, of course, but the first question you want to answer is, what are beams? Beams are structural members supporting loads at various points along the members. You can see examples of a beam right here, right? And you can see the free body diagram of it, right? Transverse loading of the beams are can be classified as concentrated, like P1 and P2, or distributed, like W. When you apply these loads, these loads will result in internal forces consisting of a shear force and a bending couple, or bending moment. And we can always find that the normal stress, the maximum stress, which is usually the critical design criteria, using the bending moment formulas we have already seen. But the only problem here is that we have to be able to determine the location and magnitude of the largest bending moments. Okay. Going back to the type of forces, we have two types of forces: concentrated load right here, which is expressed in newtons and pounds, and we have distributed loads like here, which is expressed in newtons per meters and pound per foot. So the reason I'm emphasizing this is that when you're analyzing something, you always have to be mindful of this fact. So this is not, the distributed load is usually not expressed in newtons. So it's not really loads, it's loads per unit length, right? You always have to find this area under this curve to be able to find the final total load on your beam. The other important part when designing a beam is always the beam supports. We have two type of beams: a statically determinate beam and a statically indeterminate beam. A statically determinate beam can have it can be a simply supported beam with these two type of supports, can be an overhanging beam with this type of support, it can be a cantilever beam with this type of support, and a statically indeterminate beam can be a continuous beam with three supports, can be a cantilever beam, and a fixed and a simply supported can have a fixed support and a simply I'm sorry, this was at another end, and can be a fixed beam in general. We have other types of statically indeterminate beams using the joints, which we are not going to go over. I will just have them here as examples. But the goal for us is to determine the maximum normal and shear stress, and it definitely requires, this goal requires the identification of maximum internal shear force and the bending couple. The shear force and bending coupled at the point are determined by passing a section through the beam and applying an equilibrium analysis on that specific portion or the other side of the section, right? And you always have to be mindful of the sign convention for shear force and bending couples. So let's do this. Let's talk about this type of load. Let's say we have a distributed load with this type of distribution, right? Sigma of F in the y direction must be equal to 0, which means that we are analyzing this section right now, right? Which means that your V and V plus delta V, these are in two different directions, so V minus V plus delta V minus the other force in that direction, which is W multiplied by delta X. So again, important, W is force per unit length, so you have to multiply it by your unit length to get the area covered here. Okay, so W that must be equal to 0, which means that delta V is equal to negative W delta X. That's your shear force, right? And we can always make this distance delta X smaller and smaller and transform it to a dx, which means that you're going to have a derivative. So this tells us the derivative of shear force with respect to S is going to be equal to negative of W and We can also find the difference between the shear force between two locations by just taking the integral of w dx from x of c, the location of c, which is from the beginning of the coordinate system, and the location of d. We can do the same analysis for moments. Sigma of mc prime must be equal to 0. We are going to do the analysis on this point for the moments. At this c prime moment, you're going to have an m plus delta m, right? Minus m. This force v, the shear force, will have a moment, v multiplied by delta x. And we are going to assume the total of this wx is going to be applied at the middle of this section, which is a very good assumption. You can actually take the integral and you will get to this solution as well. So the moment you're going to see is going to be w delta x multiplied by 1/2 of this delta x, this distance, right? So just playing with this, we can get to delta m equals to v delta x minus 1/2 w delta x 2, right? And we already know that this relationship exists. Your delta v is equal to w delta x. Okay, so we'll have a 1 v delta x. We'll have another v delta x, right? Right here. Which means that, or 1/2 of v delta x, that doesn't really matter for the final discussion, which means that you can find a derivative equation. If you make delta x smaller and smaller, you're going to have dx, which is your derivative. You're going to have a derivative of moment that's going to be related to your shear force. Again, going back to the design principle, the largest normal stress is going to be your maximum bending. If it happens where the maximum bending occurs, a safety design always requires that the maximum normal stress be less than the allowable stress for the material used. And this criteria leads to the determination of the minimum acceptable section modulus. Okay, so essentially, in your design, you want to find the minimum acceptable section modulus. Among the beam section choices which have an acceptable section modulus, the one with the smallest weight per unit length or cross-sectional area will be the least expensive and the best choice. Right? So let's go back to the analysis after this very short break. Let's write the equations we have had for the relationship between the moment and the curvature. You already remember that 1 over rho from the earliest, very early on in our discussion, 1 over rho is going to be equal to m of x over ei, right? We can always replace 1 over rho with the second derivative of y with respect to x squared. That's going to be equal to m of x over ey, right? So we can actually, and y, it is very important actually to note that. So this is going to be your coordinate system. This is the location on the beam, and the y is going to be your deflection, right? So this is a very important equation that we have here. We can take the integral once to get to ei dy over dx. This is equals to integral of 0 to x m of x dx plus c1, and we can take the integral twice to get to eiy, and this is going to be your final deflection, right? Because of the bending. This is going to be the integral, the double integral of mx dx plus c1x plus c2. And you always keep in mind that E multiplied by I is called the flexural rigidity of the beam. Okay, but then the question is, okay, we have the equation for the deflection, But how can we determine this C1 and C2s? These are essentially your boundary condition in your differential equation, and we can determine them using the supports. We have the analysis for the cantilever beam, we have the overhanging beam, simply supported beam, and for each of them we have the boundary conditions, right? If you plug these boundary conditions there, you can actually find the final values of the beam. But let's say what's going to happen to your analysis if you have two forces being applied, one distributed, one just regular concentrated force. That's essentially, you can always use the method of superposition. So let's have an example. Let's try to solve this example, which is an example from the Mechanics of Solids book. Right, this is telling us a cantilever beam AB is of uniform cross section and carries a load P at its free end A. Determine the equation of the elastic curve. So this equation here is the equation of, it's called the equation of the elastic curve, and this is what you want to have for your experiment, right? To be able to determine that, because you have already measured the loads, you can calculate the moments, right? When you have the equation, you can essentially relate the deflection and load. You already have those two. You can find the flexural rigidity, and if you have the moment of inertia, you can essentially find the Young's modulus, right? So let's solve this. The first part was we have to cut the beam into sections. Let's cut it into this section we have here. We have shear force, we have moments. The first thing you want to do is to calculate the moment at this location. So your m is going to be equals to negative p multiplied by x, right? Okay, so plug that in the original equation. You had ei d2y over dx squared equals to negative px. Okay, take the integral once. Okay. And then we want to find the boundary conditions. So it is a cantilever beam that goes from 0 to L. At point B, we already know that theta, which is dx dy over dx, is 0, right? So this is going to be 0. Plug that in, and we are talking about point L here. So you plug x here as L, right? And 0 is going to be equal to negative 1/2 of PL squared plus C1. So you can calculate your C1. Okay, so that's the first part. So you plug that in, your EI dy dx equation is going to look like this. But we don't have the deflection yet. We have to take the integral once more. If you take the integral once more, you're going to have negative 1/6 px3 plus 1/2 pl squared x plus c2, right? Then we have to find the next constant here. To find the next constant, we go back here at x equals to L for a cantilever beam. There is no deflection. The deflection is 0. It's a fixed support. So y is 0, theta is 0. Both of them are 0, right? Plug that in. Y is 0 at x equals to L. Replace x's with L. And your C2 is going to be negative 1 over 3 PL to the third. So your final deflection equation for this type of moment is going to look like this. It's going to be a function of your concentrated load, which is the type of load you have in the experiment you have already performed. You just play with this a little bit, you can find the deflection equation, right? But then the question becomes, what will be your maximum deflection, right? Your maximum deflection occurs where the derivative, where your theta is 0, right? The derivative of y with respect to x is 0. So dy in general, that's a general type of analysis, right? But in this specific cantilever beam, the maximum deflection happens here, of course. So you can just plug x equals to 0 and find the maximum deflection. But in a regular analysis, you have to take the derivative of y with respect to x and then find the location of that maximum deflection, plug that back in the main equation, and then find the relationship between the load and E and I and the length and all of those things, essentially. We have another example, this time for a distributed load for a different system. So you want to create a section again, but this is a little more complicated. We have the reaction force here, and we want to find the moments at this point, right? What are the forces that are applying moments at this point? We have the moment itself, of course, which is going to be equal to the moment of this distributed load, which will be Wx, right? The total force that is being applied, the area under this distributed load, multiplied by half of the length, which is x over half, and then the other moment is going to be reaction force multiplied by x. But what is this reaction force? If you just try the free body diagram first, you can see the reaction force is going to be half of WL, right? WL is going to be total force, half of it will be carried by this, and half of it will be carried by this support. So you plug that in, you have the moments, right? And then EI, d squared y over dx squared is going to be equal to the moment, right, which is this equation. And then afterwards, just the same mathematics with, of course, different boundary conditions for Cx and C2. You plug those in, you find the maximum equation. We can also, we don't need to take the derivative to find the maximum deflection here as well, because it is very obvious that the maximum deflection will happen at L over 2. But in general, your general would be to find the derivative of y with respect to x here, set it equal to 0, then that will give you the location for the maximum deflection, right? But if you had this type of distribution, you can essentially use this to find the maximum deflection. So this is all the theory we want to have. This is we talked about the structures, how the bending is present, how the bending moments are present in aerospace industry, in aircraft, and why they are important in our analysis. In our analysis, we talked about how we can do the analysis. We talked about the theory. The next part is to talk about the experiment. The experiment looks like this. You have already seen this at this point, and this is called the flexural test. In engineering mechanics, flexural bending characterizes the behavior of a slender structural element subjected to an external load applied perpendicularly to a longitudinal axis of the element. The typical material used for flexural tests are polymers, wood and composite, and brittle materials. So in your test, you have seen a metallic. You have seen a couple of metallic beams and a composite beam. We have multiple types of flexural tests, which we will discuss later in the torsion lecture. But the two main types are the 3-point bending test or flexural test, and 4-point bending test. I'm pretty sure, based on what you have seen in the lecture, you can say that this is the test. The 3-point bending test is the one we performed, right? A flexure test produces tensile stresses in the convex side of the specimen and compression stress in the concave side, right? This creates the area of the shear stress along the midline. To ensure the primary failure comes from tensile compression stress, the shear stress must be minimized. But how do we minimize the shear stress? This is done by controlling the span to the depth ratio. Okay, the length of the outer span divided by the height of the specimen, right? For the most materials, the span to depth ratio of 16 is acceptable. Some materials require to 32 to 64. It's actually not a bad idea to find the span to depth ratio of the material we use in the lab, but I definitely provide lab instructions for you, and in that I will make sure to include all of the measurements if you haven't done the measurements before. So we want to find the force required to bend a beam under a 3-point bending condition. The data is often used to select the material for parts that will support loads without flexing, right? Flexural modulus is used as an indication of material's stiffness when flexed. In this test, a specimen with rectangular or flat cross-section is placed on 2 parallel supporting pins. This is not exactly the test we did, but that's the general type of 3-point bending test. The supporting and loading pins are mounted in a way allowing their free rotation about the axis parallel to the pin axis parallel to the specimen axis, and yeah. The advantages of this type of test is the ease of specimen preparation and testing. The disadvantage is the results of testing, method sensitive to the specimen loading, geometry, and strain rate. We have 2 types of flexural strengths. The flexural test, one that tests the flexural strength or the modulus of rupture, which is the stress required to fracture the specimen in a bend test, which is not the one we did in class, right? But the flexural modulus is the modulus of elasticity calculated from the results of the bend test, giving the slope of the stress deflection curve. So for the type of test we have here, this is going to be your force distribution. This is going to be the moment for the pin supported. I'm going to provide all of these equations for you, all of the boundary conditions and everything that is. So you essentially have to apply this equation. You have to find the moment at your specific location, right, that you're looking at, find the deflection equation, find the maximum deflection, and essentially find the final equation you have. You keep in mind that you have already measured the maximum deflection. That was the idea. You should have measured the maximum deflection. But yeah, so that's it for the bending test. Let me know if you have any questions. Sorry I couldn't make it to classes today. And I received a lot of emails from you guys. Thanks for the emails. I'll make sure to reply to those emails in a timely manner. Okay.